who was at HBCSE for many years. So he has been, although he started out as an aerospace engineer, he quickly shifted to philosophy and then math education, which he has been doing for the entirety of his career. So he has moved after retirement to Bangalore. So it was an easy ride for him to come all the way here from Kengeri. So please go ahead.
Thank you. Easy and very pleasant to come back to this campus. Thank you so much, Professor Radvin, Professor Apurva, Department of Mathematics. It's really wonderful to come and give this talk. It's audible now? Yeah. So, as I was saying, Piaget brought in this cognitive revolution. So, he's quite a big figure in psychology and also is a great influence in education in general and mathematics education in particular. And one of the tasks that he's this is one of the famous tasks. So Piaget studied child development, cognitive development right from infancy. He had 3 children and he did lots of observation on them and maybe some experiments as well. So very detailed, and even the paradigm was completely different. Essentially, it involved putting some sort of tasks before the child, often with some manipulatives or objects, so that the child engages, and then you try to see the response and account for this. So this is one of the famous experiments. It's called conservation of number task. Conservation of number task. So on the left, you have some, say, marbles or toffees or whatever, 2 rows of them, same objects, marbles on top, marbles below, and they are aligned, and it's visible to the child that it's, so they are, there's a kind of correspondence. And so if you ask the child which row has more, the child will say both have the same. That's fine. Right? Then the experiment in full sight of the child spreads out the bottom row, and then asks the child which row has more. And young children below a certain age, typically 4 years or so, respond saying that the bottom row has more. Now, of course, you may think that this is a bit surprising, right? So, what are they responding to? So, it's difficult to crack this because children don't behave exactly like you expect them to. So, if you ask them like, what do you think, etc., you're not going to get very helpful answers. Huh? So, it's a challenge to so it's a challenge to figure out like what's really going on. So there have been very many theories. Piaget had his own theory, and he had this idea that there's something called mental reversibility, which doesn't develop till a certain age, and he called that operational thinking. So that the child must mentally put back the original situation and see that nothing really has changed. So it's a conservation under certain transformations. So number is conserved. Of course, length here is not conserved. So maybe they're responding to length of a perceptual thing. So one doesn't know. So to focus on the number aspect, the attribute of number, you need to be able to do this plus some other logical constructs which he tried to elaborate. But roughly this is the one. Because many researchers then said that no, maybe the child is just responding to a language game. I mean, the experimenter did something and changed. So the child feels obliged to also change the response. So this is another kind of explanation, which Margaret Donaldson, I think, and she proposed, and then they figured out variations of the experiment, which accounts for that. And then so the finding is very robust. It's been found across generations. It's now, this was done, I think, in the 40s or 50s, 1940s or 50s. So it's very, very old. It's been tested. It's quite robust across even different cultures.
Well, what happens if you like keep 2 bars of chocolate, identical bars of chocolate, and then break it up into several pieces?
So all these variations are there. Yeah. So it's a long kind of study. So but it's very clear that these abilities, for instance, to compensate for double bars, let's say, as opposed to single bars. So to get an appreciation of quantity takes some time. It doesn't come below a certain age. So that's typically.
I remember my mother used to, when my younger brother would ask for 2 biscuits, she would just break it into.
Maybe she read Piaget or something. So this is the point is that it's number which we take for granted is itself something quite difficult. Of course, number is related to counting. So counting comes surprisingly quite early. Children are able to chant the word sequence fairly early. It's probably because of culture. They all grow up, and parents are very eager that they learn fast and so on. So they teach them. It's not clear that they associate this with quantity. So let me just put this before you. So this is a task. You have to pretend it's for you. It's too easy. So which ball has more marbles? It's automatic. It doesn't even trigger any thought. But suppose I ask you, and the label says how many? Remember that. Which bowl has more? So it needs some reflection, right? Some reflection, some interpretation even. You know, it's M doesn't mean the name of the label for the bowl, but it's the quantity. Maybe it's got to do with it. So you do some processing. The point is that the alphabetic sequence is exactly like the number word sequence. It's just an ordered list. There's no, it's the connection with quantity is built over time, and it's partly cultural. And it's over use over many different contexts and so on. So for the child to begin with, it's just an ordered list. That's all, like a song or the alphabetically order or song. So it's a
of Roman numeral.
Yes, yeah, maybe I should change that. Okay, so the basic point is that they don't really associate number and counting with quantity. It happens much later. And so this was a long debate with the Piagetian tradition, including Piaget himself, I think. Rachel Gelman, she said that no, children understand number much earlier, like 2 years of age and so on. She did some experiments. And that's because she said they understand how counting works. For instance, they know that the counting word and touching some object, there's a one-to-one correspondence. It doesn't matter which one you start from, order doesn't matter. And the last number word you utter has some special significance. It stands for the whole set. So you emphasize. So these are called counting principles, and she tried to say that young kids, even 2 years old and so on, have these understanding of counting principles. So there's a kind of debate, but it's now clear that all this simply doesn't mean they have an understanding. They can apply counting to make judgments of quantity, whether comparison to say which is greater or to say whether something is equal. For example, to give you one particular experimental result. So suppose a child is asked to, there are two teddy bears, let's say, and child is asked to give toffees equally. So one to A, one to B, one to A, one to B. So you give, say, 5 toffees each, and then the child is asked, like, do they have the same number of toffees? The child is very convinced, yes. Then you ask her to ask how many does teddy A have. She counts, figures out it's 5. Then you ask her how many does teddy B have. She has to count again. So it's not. So these kinds of subtle things are being done, and there's a lot. So this is to say that this is a relatively recent paper, 2019, and so it shows that counting and quantitative comparison go in parallel, and it's only at a certain point that they actually merge. Okay, so why did I do all this? It's to give you some flavor of the developing understanding of very basic fundamental mathematical concepts. It's quite involved, a lot of research on this, and it's not very simple, and it's not, much of the instruction is not helpful. In the sense, it misses the point. It emphasizes counting. It emphasizes the symbols, writing the numerals. The quantity aspect of number, for some reason, is not emphasized enough in teaching and learning. Okay, so this is, and what do we mean by quantity aspect of number? So, okay, so you can see this diagram here. So the number sequence itself, of course, children understand that one-to-one correspondence with objects, and so it means some quantity and so on. But there's also an aspect of, see, there's a point where the number words themselves become tokens to be counted. They function like units. So suppose you say, how much is 5 plus 3? So the child will say, okay, 5, and then 6, 7, 8. So the child is actually counting the number words after 5 till 3 is reached, right? So this kind of understanding again takes time to. Not only that, to understand that the word 5, initially it can just function as a label for the 5th object counting. But then you get the idea that's the whole set. But then 5 also includes 4. I mean, 4 is inside 5. It's like a, I mean, we subset of 5, but the set language doesn't work here because, I mean, for one thing, the units are all identical, right? So membership is set membership itself. You need a distinct element. So it's not. So it's set theoretic construction doesn't really help here, but it's a kind of maybe like a psychological construct here. That there are. So 4 is embedded in 5. It's included, and so you need that to do things like 7 plus 6 is 13 because 6 plus 6 is 12 and there's 1 more. So you take the 7 and you split it into 6 and 1. And so these things happen mentally and they emerge only after a certain point. So all of this has been studied and written about and theorized. So it takes. So the overall point is that instruction needs to, you need to be aware of these transitions and the cognitive gains. Actually, they're not easy to acquire, and not all children acquire them early. And so it's good to pay attention to what's happening. Okay. Of course, there's a lot of transition beyond counting. Counting is just the, working with maybe hands and so on. So what happens to multi-unit and multi-digit numbers? So here I'm going to tell you a small story. How to multiply by 10. So the story is how much 10 coconuts cost. So 1 coconut costs rupees 35. What's the price of 10 coconuts? I mean, this is trivial for all of us, right? So you get that. But this is how a tribal adult from Bihar solved it. And this is, many years ago, a PhD student of mine was doing fieldwork in Bihar with some tribal, Mushar tribals. And then he asked them this question. So one tribal adult did this. So he said 3 coconuts cost 105. So 9 coconuts cost 315. And add 1 more, so that's 350. So this is quite striking. And of course, this particular student was extremely very excited. Arindam. He was very excited. So I got a call from this is because this is exactly the same problem given in a classic study done in the 1970s in Brazil by somebody called Teresina Nunes. And this is exactly the same response that she has recorded in her paper. So, of course, there's explanation for this.
So, there's the question, no decimal place value system or
not? So, what is the decimal place value? There are 2 aspects to the place value system. One is the fact that the numbers are arranged in multi-units. So, there is ones, tens, hundreds, which is reflected in the number words also. The other is the way we write numerals, where the position has value, which of course is not. So this is an example of what is one could call oral mathematics rather than written mathematics. So this is very prevalent in also what's described as street mathematics as opposed to school mathematics. So many people, working people, would do calculations in this way, mental calculations, without writing and without using place value, but using the multi-unit structure, the decimal structure. So this is Teresina Nunes' study in Brazil. And so one of the findings was that, I mean, this is very famous, the whole concept of street mathematics, because she found these street vendors were children and she would give them problems and they would solve it. The same problems, if you present it to them just by numerals, like in a school book fashion, they would fail quite miserably. So this is a study done in, I think the paper is 1977. So that's the 1985, sorry, but it was done in the 70s. And very recently, this has become, you would have probably read about this in the newspapers, because some Nobel laureates have suddenly discovered that this is what happens. And there's a paper in Nature. This is an India-based study by Abhijit Banerjee, Esther Zaflo, and so on. So they found out that, yeah, children do, working children particularly, they find they can do problems easily, but not if you present them in the school book form. And Arindam's work, PhD, was all about this. He worked with children who were used to doing various work contexts in Dharavi in Bombay. And so they, neighbors, families had things going on at home. So they were quite used to making lots of calculations. It was a very, very interesting study.
So can I ask, this tribal village, did they know the multiplication code? And did they quickly know that 35 times 3 is 105? Or
I think they knew multiplication tables, but not of up to 35 and so on. So that's a good question. So in fact, so why is it that it was exactly the same response in Bihar and in Recife in Brazil? So the one explanation is that they have these landmark values, like 100 is a landmark. You can work with mentally. So you try to reach 100. And then so it becomes a stop and then you calculate it. That's the proposed explanation for that. Of course, this is something that I like to show to teachers, that, a good understanding of place value requires also certain vocabulary. So the fact that the value of each unit, whether it's a unit or a 10 or 100, each of them, the value goes up by 10-fold. So what happens is that the ones become tens, the tens become 100. And then the way to do that is to, of course, shift the place. And that's what the 0 does. Putting the 0 kicks the place value up by 1. And so that's how it really works. So this is okay. This is my next example. I'm measuring length. And so, I mean, you would think that this is really simple, right? Measuring length with a scale. So, nothing can, hardly anything can go wrong with it. So, let's look at some student errors. So, what you do often is to change the task a little bit to test whether. So, this task is, kind of a little bit changed. And you have to find the length of the pencil, and those are the options. So the actual length of the pencil is, you can see, is how much? It's 5 centimeters, right? So the options are 4, 5, 6, and 7. So what do you think children chose? Class 4 to class 6. Okay. Okay, so we'll figure out 6 and 5 and 4 and 7. So 5 is the correct answer. Someone said depends on the context, right? Which schools? What kind of schools? So you're going to find this very interesting. So this is the percentage of students, and the number is very, very huge. It's some thousands, I think. Tens of more than 10,000. So the sample size is huge enough. So it's a very, very robust finding. So you can see that option B, the correct answer is only 15%. Right? C and D seem to be the preferred answer. But just remember that even option A, some kids have given. So we need to account for all of these. So what really is going on? Okay, so I'm going to show you a video, which it's from the same study. It's by Educational Initiatives, which is a sort of educational organization, does assessment, work in assessment and testing. And this videos, I think they're on YouTube, so it's should be available publicly. It's a government? No, it's a non-government. It's an NGO. Okay, so we go to the first video. I hope everything goes well, sound-wise and so on. So we'll play the video in full. Pay attention. And if you need, we can do it again, but there won't be that much time. The same example. Okay. So, what are your comments?
So one question, when this experiment was conducted, like were those other students in the same group?
Yeah.
So like, isn't there a possibility that they might be repeating what other students have asked?
Possible. I mean, the persons in the video are pretty skilled, I would say. I mean, you learn. So I think those effects you can, I would ignore. It's not that. So because so there are different kids saying different things. It's not like they are.
Many of them are saying 4 is 1, 5 is 2.
There were different responses. If you noticed, some of them were also correct.
Yeah.
And some of them, in fact, yeah. But let's take maybe some different. I think there might be in this video 1 or 2 schools. I think. Even 1 or 2 schools, not too many the variation, but the study was
different.
yeah, the instances were different. But the study was conducted in a very large number of schools. Yeah.
It seemed like when the pencil was way farther, so when 9 centimeters was more absurd of an answer, they were more careful.
Possible. Yeah. Yeah. It's a nice observation.
I mean, was that just the way the video was made, or did it actually reflect?
That effect might be there. I mean, if it's closer to the correct answer, then they are more likely to make an error. If it's further, they're less likely. That's possible. Yeah. That's excellent.
So this question about how much is 1 centimeter? Actually, the diversity of answers does not surprise me. And I think there's some connection with the correct answer arrived at what most of us in this room would consider a counterintuitive algorithm. This was the price of 10 coconuts problem. And I wonder whether language sense and number sense are sufficiently different that a lot of the diversity of the answers are coming from the fact that you're putting a child on the spot to explain what this number is. Because I'm almost certain if I was of that age, I would be able to measure the length of the pencil correctly every time, independent of the measuring device given to me. But I may not have been at all competent in explaining why I did what I did. That's number 1. And number 2, maybe answering in a way that was clear to the listener what I thought 1 centimeter was.
Yeah. I mean, let me respond to, you're right about doing a task correctly and giving an explanation for why one. There's a divergence. There can be a big gulf. But it's also true that, I mean, while some students do get it right, the majority of students in different kinds of tasks do get it wrong, including tasks where they're given measurement. Of course, I think if you're given a proper scale and a length to measure, usually you get it right. But the way, if you modify the task, for example, you give a broken scale, this is very common. And then they have a problem and the response is often wrong.
So sorry, this were they first asked to mark their answers on a piece of paper, and then
this was 2 independent things. One is a written test in which there are many questions, and so the response rate I showed earlier was from the written test. And this was followed up with this sort of group interview in the classroom. It's a typical kind of pattern for many studies. You do a written thing, collect responses, then try to find out what's the thing.
So do adults almost always get the answer right for this question?
I don't know if there's a study, but I expect that people who use the scale in some meaningful context, like say in a physics lab or somewhere where you need to, would get it. And then you're right. I mean, after a certain age, the responses settle down. So what age is that? It's interesting. So if you notice, there were 2 major kinds of errors. One is what's called the endpoint understanding, right? So the number that you read off the scale, I mean, the scale is some kind of a magical device which tells you what the length is. This might be a way of describing that understanding. It's like a dial of, say, some electric meter, galvanometer, ammeter or something. So whatever the reading is, that's the value. So this is, so the construction of the scale and the principle of measurement that goes into it is hidden. It's not at all obvious. And so it's just like a device by which by convention we use to read off the length. The other thing is that the students do have some understanding that it's the length. And they may count, you saw them counting the tick marks, right? Which are equally spaced. So probably they have an intuitive understanding that that's actually measuring length in some way. And so that was, so these are two different kinds of errors. And it's,
The second one is noisier. What did you mean? What was the second error? You didn't complete it.
the second error is counting the tick marks, not just reading the endpoint of the off by one. Yeah, off by one. Sometimes they count the smaller tick marks, and sometimes I don't know why. Did you account for why some kids chose 4? Because they leave out the last end marks and just count the ones in between. 1 or 2 kids did that.
Some people count both.
Yeah, counted both and some.
Has this experiment been done with a ruler with markings but not numbers?
Yeah, so all kinds of variations have been tried and can be tried. So the point that, okay, now a little more about this. So this is class 4, class 6, class 8. Okay, so this is, so those are the numbers. And you can see that the percentage of students who gave the correct answer, that's in green, it's going up sharp. So it's settling down. So it reaches by class 8 something like 65%. But still, kids are doing error, making an error. And the endpoint rule is coming down sharp. So that's almost disappeared. How the most interesting is the counting that it's not coming down, it's kind of staying on. So one thing that, yeah, of course, it's good fun to watch these videos because it's amusing to see kids making all these errors. It gives us a kick. Right? I'm saying it's good fun watching kids, making a fool of themselves like this, and so we all enjoy it. And by the way, I mean, to your question, these were actually done in what were identified as elite schools in metros.
I realized because of the English accent
And the uniform and so on. And many years ago, in 2008-9 or thereabouts, it became a cover story in India today, this particular study. Because it was done and they had a way of identifying the elite schools by talking to parents and so on in, I think, 5 or 6 metros. So it's called the metro study. So I mentioned this because, see, even teachers had this response to this video. They're amused, partly. Partly they get worked up, because they start to wonder whether their students are also going to make the same. They get anxious. And the response is to now get hold of the kids and to hamper this. That, that this is the way to measure. So, which is not the best kind of response. So the point is to understand also what is going on in the child's mind. And the kids are all quite intelligent. It's not like they are giving fairly articulate explanations, many of them, even if they're wrong. So they're picking up something from the environment, putting it together in the root way. I mean, all this is becoming more sympathetic to what's going on in the child's mind is a consequence of the Piagetian tradition. You try to say that they're rational human beings. They're doing some kind of logical thinking and understanding, and they're working their way through putting together various inputs from outside. There's a famous science understanding of the Earth, round Earth. I don't know if you all know this. So they study because the experience of children is that the Earth is flat. Right? But they keep hearing from adults, textbooks that the Earth is round. So how do they reconcile this? It's a very interesting thing. Some of them think Earth is like round like a chapati, like a disc or something that it's like a fish bowl, and they're inside the fish bowl, on something flat. And then the rest of and the most interesting thing is something called the twin Earth model, which is that the Earth we live on is flat, but there's an Earth which is round, somewhere. So that's anyway. So these children are actually rational. So what we do is that we do this little bit of exercise, which is, I think, kind of evident to you. Some of you already said that, but not a familiar way of thinking for mathematics teachers. We say that, okay, see, let's take the most persistent error, which is that you count the interval. Count the tick marks, and say that that's the way we do length measurement, because it is, it gives an idea of length. So what's the issue?
It was discrete data that they would count 6. Six human beings, you would say there are 6 people.
Right. So we go a little ahead, with this and say that, okay, if we adopted this system, this as a measurement system, then what would happen? Now, of course, what happens is that, there's just, you add one, so one more. So there is a,
0 becomes 1. That's
Yeah.
the first problem.
That's
Zero
the problem.
becomes 1.
So of course, order is preserved, so comparisons are always possible. Then we ask them that what happens with addition. Addition doesn't work. And so what about multiplication of the length by a number? And what about multiplication of two lengths? More messy. What about division? And so on. So this takes a while to respond. What about division by a number? And so, of course, you want us.
It's not even well-defined, right? You move the pencil a bit, its length changes.
No, this is counting the tick marks.
Say that is fine.
Yeah. You have to, if it's between 2 marks, you have to do some approximate, which is the case anyway. If you're working up to, if the
But
zero error is 1 centimeter.
From my school experience, you learn about things like least count of a scale much later. So you have the scale, 1 centimeter to centimeter, whatever, maybe that was early. But I remember only in 8th standard learning the concept of the least count.
Yeah. Of course, we learned to measure in 0.6, 6.3, 6.2, etc. earlier. But you're right. Becoming aware and consciously aware of this. Okay. So we ask the teachers to reflect that measurement system should work not only for comparison, but also for operations, arithmetic operations that you do. There must be some kind of a mapping of what you do in terms of arithmetic operation and what you do in real life, whether it's joining or replicating or equipartitioning, and so on. Okay. So so we go a little more. I have, let me see. Just a minute. So I think, so we can skip some examples. We want to do this one and then take a break. Yeah, maybe. Then we can have a shorter second session.
We started 10 minutes late.
Okay, so we can. So this is from a study from one of my former PhD students, Shika Thakur. So this, she was studying, this was a study where you work with teachers. So it's a teacher professional development intervention. So you observe classroom lessons, discuss with the teacher what went on. And so very interesting. And I'm going to talk about one more example later after the break from the study. But this is about decimal numbers. And this is something that cropped up in the lesson she was observing. So this teacher is teaching decimal numbers more or less for the first time, decimal fractions. 683.1. So she explains that just as there are tens, you have tens. Just as you have hundreds, you have hundreds on there. So all these place value, etc. she's explaining. And then the student asks, some student asks, so student 1, once. Then student 2 says, once nahi hota chal. And the teacher appears to ignore, at least from, it was not clear that whether the teacher heard it and ignored it consciously, unconsciously, no response from the teacher. Now, the study involved some kind of working with the teachers and then doing it again in the second year. So year 2, the same, so this was done with 4 teachers. So there were 8 classes in which the same lesson was done, decimal numbers. And in 6 of them, this question cropped up. some kid or the other asked about once. These are regular classrooms, I mean, 30 to 40. So in year 2, however, when the student asks, "Ma'am, once क्यों नहीं होता है?" So the teacher paused. Nikita is asking, why is once not there? Then student says, 2 says, "Ma'am, hota hai." Then a long discussion ensues on why once are not. Okay, so we'll not go into the discussion in great detail, but just try to understand why. I mean, this is an example I do with, again, use with teachers. So what's involved? And one of the, so why are the students asking this? What's going on in their mind? Secondly, is it important to intervene or to ignore and move on? This is a thing, that decision that teachers have to make. So there is some kind of a construct which is called pedagogical content knowledge. It's a very important idea, concept. The idea is that, teaching, the knowledge you need for teaching is not just about methods of teaching. See, when you go to, I don't know if you are aware of what goes on in a B.Ed program. So in a B.Ed program, which is done after teachers do a BSc, BA, etc., you acquire a basic degree, and then you do a B.Ed for 1 or 2 years. Now it's 2 years. It used to be 1. And in the B.Ed program, you are given teaching practice and teaching skills, pedagogy. So they're called methods. So there's typically a methods course, maths methods, science methods course, etc. And in which you take the content and you package it into, there are some, 20 methods which are well defined in some textbooks. Some others may have some other list. And then you frame this content into that pedagogy. And you do your practice, you make lesson plans. However, this idea that pedagogical content knowledge is that pedagogy and content can't be separate. They're very closely intertwined. You can't take the content and put it into a shell of pedagogy and then teach. That's not the skill that the teacher needs. What the teacher needs is to understand the content from the perspective of teaching. What's important. Like the things I showed earlier, measurement and so on, are unimportant for scientists, physicists, engineers. They don't need this knowledge. But it's important when you have to teach kids. So that's what's called pedagogical content. So specialized knowledge for teaching, which is an amalgam of pedagogy and content, and it's proposed by somebody called Schulman. It's become a big thing in teacher education. So this idea is that this example that I showed once, part of the knowledge is mathematical, part of it is sort of psychological. What metaphors children used. So this is more the psychological part. The decimal point is like a mirror, and the way the teacher is teaching is, there's tens and there is tenths, and there's hundreds and there's hundreds. So it's quite natural that in 6 out of 8 classes, kids asked, where is the ones? So ones is missing. It ought to be there. But the mathematical structure shows that the location of the mirror is somewhere else, right? It's the exponent notation, for example, shows it very clearly that it's the ones. The units are the kind of anchoring thing, and then you have things which are smaller than the unit on the right and bigger than the unit, and it's a kind of pattern. It's a regular pattern in the decimal place value. Okay. So both of these are in some way important. Of course, the teacher takes both of these, and then it's not like she's going to teach the kids that look, there's a mirror here, etc. No. So the way you do it in the classroom can be very different. Like I mentioned that in year 2, this question propped up, and the teacher actually discussed it, and it was a very interesting discussion. So a bit of it is this, yeah. So she threw it back to the children, right? And they asked, so why are there no ones? So some children came up with, I think, a couple of explanations emerged. This is one of them. So one kid said that, okay, suppose there are ones. Let's say there are ones. one-eighths. And then there's a 7 one-eighths. But we know that the tenths are written like 1 by 10. So 5 tenths would be 5 by 10. So 7 one-eighths would be 7 by 1, which is the same as 7. So it's a unit. So it will come on the left of the decimal place. So this kind of discussion was nicely managed, choreographed or whatever by the teacher. And this was very fruitful. So it's reported in that paper along with many other things. Okay. Okay, so we can take a break now and then come back. 10 minutes, right?
Yes.
This is for the online course. 10 minutes we reconvene.
This noting.
So you can say it's a case of bad notation, right? We have mathematicians chosen a bad notation for decimal.
Decimal.
Decimal